All right, we're going to talk about the Diels-Alder reaction. We talked a little bit about the Diels-Alder reaction in class on Monday, and what we talked about was regiochemistry. We talked about which atom on the diene is going to react with which atom on the dienophile, and I've summarized that up here. So the regiochemistry, the rule we're going to use for this is the orthopara rule. So the most electron-rich carbon on the diene reacts with the most electron-poor carbon on the dienophile, and that's how we're going to figure out the regiochemistry. We didn't talk at all about stereochemistry, and that's the other key component of the Diels-Alder reaction. And the stereochemistry and the Diels-Alder reaction, we have several rules that we have to follow, and so we're going to take a look at each of them. There are three that we're going to look at, and that's going to help us solve the problems that you're looking at for class tomorrow and that we're going to work on in the future. So the first one is that the Diels-Alder reaction is stereospecific with respect to the dienophile. So what does this mean? Let's take a look at two different reactions. Right, so in this case, we have a dienophile that is a cis alkene. And then let's look at, so that'll be reaction number one. And then let's look at the same reaction with a trans alkene. Right, let's see what's going to happen in each case. So we have a cis alkene here, trans alkene here. Right, if we react the cis alkene, those two groups are going to be cis in the product. So cis goes to cis, and then similarly when we react trans, trans is going to go to trans. Right, and like we mentioned in class, we're forming stereocenters. This is an achiral molecule, it has a plane of symmetry, so it's going to be this one plus the enantiomer. Again, we're going to get the trans isomer here, right? So it's stereospecific with respect to the dienophile. The reaction is also stereospecific with respect to the diene. So let's look at two reactions to illustrate this point. Right, so if we have this reaction, we heat it, we're going to focus on these two methyl groups. Right, so these things are what we'll call pointing out from the diene. That's where the new stereocenters are going to form. Right, we're going to form that compound where these two things are pointing out. They end up cis in the product. Now, if we take one of these methyl groups and flip it over, so that we have one pointing out and one pointing in. And we do this reaction. we're going to end up with a trans product. Okay, so those rules I hope are relatively straightforward. One thing that we can also do, just to be clear, is to make sure that we're drawing our mechanism arrows. So again, we're going to connect those carbons, so make sure we add those curved arrows to all of the reactions. And make sure we're clear where we're forming the bonds. And again, the Diels-Alder reaction is always going to form a cyclohexene. That ring should always be drawn flat, and the substituents coming off it should be drawn either coming out or going back, just like we've done on all of these. And note that in this bottom case, we've illustrated how you can use an alkyne as the Dienophile, which is another useful extension of the Diels-Alder reaction. All right, so we've illustrated these two rules. We have one more rule to illustrate, and then we'll do a practice problem. The third component of the rules for stereochemistry is the Alder-Endo rule. And this is going to allow us to answer questions like the following. Okay, so the question is, how do we predict what's going to happen when we have a reaction that looks like this? Right? So we have a methoxy group on the diene, a ketone on the dienophile. The question we want to answer is, when we do this reaction, those two groups end up cis in the product. And again, it's this plus the enantiomer. Or do they end up trans in the product? And clearly, if this was something controlled by sterics, we would get trans. Turns out when you run this reaction, you get the cis compound. So this tells you that this is controlled by electrons. And this one is not formed. Okay? And let's just write out how we can state this result. Okay, so one way to state the Alder-Endo rule is that the W group on the dienophile ends up cis to groups pointing out on the diene. Right? And clearly, we need to answer why. Otherwise, it's just we're memorizing a random fact. Right? And the why is something called secondary orbital overlap. Right? And secondary orbital overlap is an interaction between the dienophile W group and p orbitals on the internal carbons of the diene. Right? And to get a really nice picture of this, check out page 789. Klein has a really nice illustration. Right? We'll talk more about this Alder-Endo rule in class, right? Because this is the more complicated of the stereochemistry rules. And what I want to close with is putting it all together. Right? So we're going to do a problem, put it all together, and then we'll talk more about this in class tomorrow. Okay, so here's a problem where we can put it all together. Right? Here's our diene, here's our Dienophile, and the question is, what's the product of this Diels-Alder reaction? Right? So let's come up with a strategy for doing these problems. Number one, we always have to consider regiochemistry. Right? And remember that regiochemistry, we're going to worry about the ortho-para group. Okay? So we're going to look for the most electron-rich carbon on the diene, the most electron-poor carbon on the Dienophile. Those two are going to come together. So if we look at this, hopefully we can predict that this is going to donate electrons in. It's going to make that carbon electron-rich, that carbon electron-rich. If we look at the Dienophile, NO2 is going to pull electron density towards it. It's going to make that carbon electron-poor. We want to match up electron-rich with electron-poor. We have to flip over the Dienophile. Right? So let's rewrite the reaction that we're going to do. So that we get the correct regiochemistry. We're going to form our cyclohexene, and initially, don't worry about stereochemistry. All right, so just get all the groups in the right spot, and then we can figure out what we're going to do in terms of the stereochemistry. So number 2, stereochemistry. So we're going to do stereospecific with respect to diene and the Dienophile. And if we do that, if we look at the Dienophile, the NO2 and the ethyl group are going to end up cis. So those two groups end up cis. Now we have to figure out what's going on with the methoxy and the deuterium. Those, one's pointing out, one's pointing in. Those are going to end up trans. So we have two different options for how these are going to play out. So methoxy and deuterium are going to end up trans. So our options are the following two. So the question is, do we end up with the methoxy and the nitro cis or the methoxy and the nitro trans? Right? And the way we figure that out is to use the Endo rule. And again, the Endo rule states that the W group ends up cis to groups pointing out on the diene. The methoxy is pointing out. So this will be our product. This is the Endo product. So it's that compound plus the enantiomer, right? And that's our goal, is to be able to go from this complicated Diels-Alder reaction down to what the product is going to be, applying these rules of regiochemistry and stereochemistry, right? And we'll also learn another way to do this. There's a Diels-Alder drawing tool, and we'll talk about that in class tomorrow.